So the next subtopic of astrophysics is about blackbody radiation. So if you remember, we actually did a unit on blackbody radiation, so this is going to be a good review. But here's the thing with the blackbody radiation. They use different terminology in astrophysics as they do when we talked about it before with just general concepts, which is annoying, but it's the same exact thing, it's just different terminology. So let's talk about the differences here. So one thing to note for sure are distances. The distances are vast different distances we talked about. So a parsec, light year, AU, those are distances that you have in your form of packet that you can use as far as like distance away. Because remember, intensity, as you get farther away, the intensity goes down. So we can use those distances to figure it out. Now, in the very first page of your form of packet is something called a solar constant, capital S. This is equal to 1.36 times 10 to the third watts per square meter. This is defined as the amount of the intensity of sunlight on the surface of the Earth, ignoring any dissipated energy. So it's like how much sunlight, the maximum sunlight that the Earth could get if there's like no clouds to block it or anything. Like this is like the maximum sunlight that we can get. So that's the amount of sunlight that hits the Earth. So here's our equations for this little subtopic for astrophysics. The first one is luminosity. L stands for luminosity. Essentially like how much power or how bright the surface of this object is. Like how bright is the surface of the sun? How bright is the surface of Sirius A or Polaris, whatever the star is. So the equation is luminosity is equal to Stefan-Boltzmann's constant, which is another constant on your first page. It's 5.67 times 10 to the minus 8th times the surface area of the object, the star probably, times the temperature to the fourth. Now remember, we did this exact same thing with blackbody radiation, except we called it power. We didn't call it luminosity, we call it power. The power was equal to the constant, Stefan-Boltzmann's constant, times the area, times temperature to the fourth, times the emissivity or efficiency. How good is it at actually sending out radiation? Well, if you notice, there's no efficiency factor here because we assume that stars are 100% efficient at sending out radiation because they are entirely radiation. They're like 99.99999% radiation. What's the other small percentage? It's dissipated energy, I don't know, whatever. So absorbing some energy, light into the molecules, whatever. But it's sending out radiation. It's good at it. Other things might not be as good, so it's an efficiency factor there. So these are essentially the same exact equation. Nothing new. Nothing new. Constant, area, temperature to the fourth equals power, or luminosity. So we're just calling power luminosity. It's measured in watts. What do you know? Now, when we talked about intensity before, intensity is power over area. For astrophysics, they call intensity brightness. How bright is it? And it's also measured in watts per square meter, just like intensity. It's literally the same thing. If you take the power equation divided by area, remember area is 4 pi r squared, or in this case the distance away from the star squared, you get exactly the same equation. Luminosity is power, 4 pi r squared, r being distance, is the brightness or intensity. So brightness is the same thing as intensity. Luminosity is the same thing as power. So it's the same equation. Power over area, 4 pi r squared. So these are the same equation. Then Wien's law, if you remember, was a relationship between the wavelength of light and the temperature. As the wavelength of light goes up, the temperature goes down. So we always did it as lambda max, the peak wavelength, the maximum wavelength it's measured, is equal to 2.9 times 10 to the minus 3, or sometimes it's labeled as B. They just call it a variable B, it's a constant, over the temperature in Kelvin. Well, all they did was they took that equation and multiplied both sides by T, and they rewrote it. So these are exactly the same equation, just rewritten in a different way. So I don't know why they changed up the terminology, but they're exactly the same equation as what we did for blackbody radiation. That's the only difference. That is literally the only difference between those equations in the astrophysics section and the blackbody radiation equations we used before. Just using the same equations, different variables, different terms, same equations, right? So let's go over another example using their equations and their variables and their terminology. So remember doing this? We did intensity versus wavelength. This is for our sun, by the way. So the peak wavelength is 500 nanometers. That's the measured peak wavelength. So notice how it maximizes at that point. That there's more 500 nanometer light given off by the sun than any other color. So 500 nanometers. So question A, we want to find the surface temperature of the sun. It's not the temperature of the core of the sun, it's the temperature of the surface. So we need to figure out which equation to use. Well, we need one with wavelengths, then look at this. We can use this equation. But let's use their version of it, that. So 510. Now we need to, the wavelength max is 510 nanometers, so we have to multiply by 10 to the minus 9th times t equals 2.9 times 10 to the minus 3. We can divide both sides, not 510, it's 500. We could multiply both sides, or divide both sides by 500 nanometers. What's that equal? 500 times 10 to the minus 9th. So the surface temperature of the sun is roughly 5,800 Kelvin. This is an approximation, 5,800 Kelvin, done. Luminosity, which is the same thing as power, we could literally use the power equation. The emissivity of the sun is 1. So the power of the sun is just Stefan Boltzmann's constant times the area, which I wrote here. Here's the area of the sun, surface area of the sun, times the temperature of the force. We found the temperature, or luminosity of the sun is exactly the same equation. So luminosity, 5.67 times 10 to the minus 8th times the area, 6 times 10 to the 18th times temperature to the fourth, 5,800 to the fourth. So we get some huge numbers here. That's another thing about astrophysics is you get some astronomical numbers, numbers that are just ridiculously big to fathom. Like what is, well, what do I get here? 3.85 times 10 to the 26 watts. That's how much power the sun has. That's a lot of watts. I mean, it's just ridiculous. Or the luminosity power of the sun is that. It's crazy. What's the brightness of the sun on the surface of the Earth? So obviously, it's not that many watts bright because we're far away from the sun. We need to use this equation, intensity. But one nice thing that they did for us here is they told us what the area was. Rather than plugging in 4 pi r squared for the area, they actually told us to use 4 pi d squared. So to figure out the brightness, how bright it is, or the intensity in watts per square meter, we would take our luminosity, 3.85 times 10 to the 26 over 4 pi, and then for the distance, we need to use the distance in terms of meters, because we want watts per square meter, and 1 AU is equal to this many meters. So we have 1.5 times 10 to the 11th squared. So make sure you put parentheses around stuff because your calculator is going to mess this up. Order of operations is important for astrophysics. So divide by 4 pi. Yep. And then divide by 1.5 times 10 to the 11th. Squared. So I get that this is 1361 watts per square meter. And you know what? This is the intensity on the surface of the Earth. We actually knew what the answer was before we even started because that is an unknown value. So that's what the solar constant is, 1.36 times 10 to the third, 1.36 times 10 to the third. So we got the right answer. Well, how would the brightness change if we were 10 parsecs away from the sun instead of 1 AU away from the sun? So is the brightness going to go up or down? Well, instead of 1,000 or so watts per square meter, it should be a lot less because you're much farther away. So you use the same exact equation as before. Brightness or intensity is equal to the luminosity or power times 10 to the 26 over 4 pi. But now we need to figure out how many meters 10 parsecs is. Well, a light year is this many meters, then we multiply by 3.26 to get the parsecs, and then we have to multiply by 10 because there's 10 of them. So that's going to be a lot of meters for 10 parsecs. So 9.46 times 10 to the 15th times 3.26 times 10. So 10 parsecs is 3.1 times 10 to the 17th. We still need to square that number. So, oh boy, crunching the numbers again, we get 3.85 times 1026 divided by 4 pi in parentheses, and then divide by 3.1 times 10 to the 17th, and then we square that 3.1 times 10 to the 17th. Make sure your parentheses around that, and we'll get the difference. I get a brightness of 3.2 times 10 to the minus 10 watts per square meter. So, I mean, it's not even the same ballpark. You got a little over 1,000 watts per square meter, and this is 10 to the minus 10th, or 3 times 10 to the minus 10th watts per square meter. So that's a million. That's 10 million times dimmer when you're that far away. You wouldn't even be able to see the sun. It wouldn't even register for any sort of glow in the sky at that distance. Definitely not to the human eye, and probably not even to our highest technology. We wouldn't be able to see the sun at that distance. Where if we look directly at the sun outside any given day, you could hurt your eyes. So, what a difference. All right, that's a review of blackbody radiation in astronomy terms. So, that's how it works.